Okay, the first thing you have to do to create a FANUC iRVision inspection is to build a camera, what they call a camera setup. And you'll open up your normal FANUC browser here, click on Vision Setup, and you'll see there's quite a few files in here. Please disregard all those. And you're going to go to V-Type here, and you see Camera Setup Tools. Select it, and you're going to create a new one. So you're going to use the Create button down here. And this is pretty simple. There isn't much to setting up a camera. The type of camera we have is a Sony analog camera. You know that by the last session where we looked up the camera information. And you're going to call everything, every file you set up in here, you're going to call by your initials, which I'll just use as XXX camera. And you can put a comment in here, 2021. You click OK. And then I'll either double click on this or click Edit to open up the camera setup that we just created. And initially you'll see probably just maybe nothing, all white. What this really is, a camera setup, is to make sure you're communicating correctly with the camera and to make sure that you can actually use this camera setup as regarding its focal length, field of view, and lighting that's available. So I look at this and I know that it's too bright, so I'm going to knock it down a couple of stops, and I notice this is a good setup, and I've worked on this, so it looks very much in focus as well. So these are the kind of things that you'll see in the camera setup. I'll save this and then end this edit, and that's really all there is to do in a camera setup. I'm going to pull the lab up that we have here, the inspection lab, to help follow along. We'll need this documentation to know what we're doing. So the next thing we're going to do is get out of, if you remember, we were in V-Type camera setup. We want to get now into the process, the process tools. And within it, we're going to look for an inspection process. So that's what we're doing now, is building out the inspection now that we've built up or set up the camera. So this is process tools, create. Within it, we don't really want the vision process yet. That's for creating offsets. What we want is the inspection vision process, single view inspection process. Again, you're going to use your three initials and call it copper T, and comment. Again, I'm going to put 2021 just so I know what, and I'll click OK. File is already in use. I'll call this underscore. Okay. And copper T 2021 is this right here. I can either select it like I have right now and click edit, or I can double click on it. Once I do that, I see that there's a part of a process already built out. I've got the evaluation tool, which is always going to be something that it needs to either allow it to pass or fail. Clicking on the tree that we have here, we have a way of building out different processes, and we're going to build it out to be just like we have here. That's our first goal, is to actually set that up so that this looks just like this. I begin doing that by being sure I'm clicking at the very top of the tree, and I go to this section right here, which will be new, a new process. I click on it, and I don't really, even though I have a GPM locator here, I don't want to select that right now. In fact, I want to select the Window Shift tool, which is right here. And then I click OK. And you notice that with the Window Shift tool builds in a GPM locator, geometric pattern matching locator tool is placed within the Window Shift tool. The Window Shift tool allows other tools to use this GPM. It's a little confusing, but that's basically, just think of it as a way of allowing this GPM to be shared by other tools that you're building in the tree. And then we'll move on to do the Edge Pair Locator. So again, we have to go up to the top of the tree, select Edge Pair Locator right here, and OK. And notice now I have the same exact structure that's listed in your in your lab documentation. So we've got the single view inspection, the window shift tool, and then the GPM locator underneath it within the window shift tool. Then we bounce back to this main branch here, and we have the edge pair locator tool and the evaluation tool. One of the problems you'll come into and have is by possibly putting these tools under all the window shift tool, or just not having the right subdirectory layout like is shown here. Okay, our goal now is to make this red screen green. Basically, this is red because it's not finished. When it's finished, everything will be in green. There's nothing to do for the window shift tool. That's why it's in green already. It's completed. So if we look at this, we have to select a camera setup. Well, we just did that, and I'm going to go over here and select our XXX camera. And you notice that suddenly we get some more green here. And this is my camera setup here. Now everything that I do for this camera setup actually is saved. It's not just to test it out, it's actually to save these settings. And I know that I'm too bright now, and I'm going to click down a few stops to actually lock in. But this is where I'll probably need my actual target, my product going by, to actually get a good feel for whether I have the correct exposure. To do that, I'm going to click the live view here. And then I'll place my copper T in the correct orientation just below the camera, again in a horizontal way where I like to measure the actual inspection. Once I've done so, I want to make sure of a couple of things. One is contrast and focus, and a few other things too, but I want to make sure I have enough contrast, which I've set this background up to be very bright because I know I'm dealing with a dark target. My product is much darker than if I, on the scale of, there's really a scale of 0 to 256 with an 8-bit camera like we have. So 0 being completely black, 255 being pure white. This copper T definitely leans more toward the darker side. So I'm looking for a white background. I'm using a pretty bright background, not actually white. This is a black and white camera. This image back here is actually yellow, but it's appearing as mostly white. And giving me the contrast then. So I've got nearly 255 background and a pretty dark target. This will give me edges that I can work with. Second is my lighting. My lighting is what's made this so bright back here and yet not bleached out my target. I wanted to brighten up the background, but I wanted to leave my target still pretty dark. I do have some issues with some reflections on the target, and that may be an issue, but I think I'll be able to get by with it because I could see there's enough contrast between my edges. Second is, or third I should say, is a shadow that I've created with my lighting. My lighting is obviously coming from this top direction toward this direction, but that won't be an issue because I'm not measuring from here to here. I'm measuring across the long side of the T. So that shouldn't be an issue that I've created this shadow over here, which it's pretty hard to get away from shadows. Unfortunately, there's tricks to do that. We'll talk more about that during lighting setup. But for the most part, I'm liking this setup. The building structure for just about any iRVision, plane inspection or an offset, is going to be a good GPM, a geometric pattern match. And that's the next thing we'll actually build out here. So I'm going to double click on the GPM locator tool, and then you'll notice that there's a whole subset of tools here that we're about to go through, and the first of which is I want to teach a geometric pattern match. When I do that, I'm going to get a window that it wants to inspect. So I'm going to set that up around this, and basically I'm setting up my standard for what I'm going to be looking for when I do a vision inspection. This better be a good T, in other words. I don't want a T that's too large, too big, deformed. I want what is like the gold standard of my product in here. And so I've selected this window, clicked OK, and you notice I've got quite a bit of the green outline here is, let me pull this over a little bit and expand. If you can see, there's a green outline to show where it's found edges. But it's also found them within my product here. So I really want to get rid of those, and that's what we're going to do next, is actually mask those out. We're going to create a training mask, and I'm going to click on this right here, and then select some drawing tools to actually create a mask. A mask is just saying ignore these areas of my master, the pattern that I'm teaching. Ignore these areas. I don't really care about the inside of the T. All I care about is I click the draw there, and I like using the box tool for a rectangular product like this. So I'm coming down and creating another box tool and just selecting inside the edges, and again click draw, click OK, and now you see I've masked out all that information. So now when the iRVision process recognizes this T, it's going to ignore all the areas I've shaded out here with this mask before it begins to do the processing. Okay, by this time we've done a bit of work here. We notice that we're pretty far along in making all this green. If I look now, the edge pair tool is probably the next thing to work on, but this is probably a really good time to save. So just keep in mind, if somebody would have shut off your robot controller, you'd lose all the information you've done up to this point if you have not saved. Okay, so let's set up the edge pair locator tool. To do so, you must have it selected. Can't be selected somewhere else like up here. You have to select on the edge pair locator tool, and then you can come down to the search area. You can set it up. It's not, you can see it's red, it's not trained right now. And set it up and drag it along here and set it up across the edges that I want to inspect to determine the length of them. So I'll say OK, and then I'll save again. Once I've done that, I want to actually train it. And here I'm looking at the edge to edge that I want to actually train, and I'm looking here, I have two edges over here, so I may not be in the best setup for training this, but I'm going to use this anyway. But this is a case where I would want to set the product up so that I was actually looking at only two edges here. What this means is that my T is a little bit too far to the left of the screen. If I shifted it to the right, I wouldn't see the bottom edge. What I'm seeing right here is the top edge, and over here I'm seeing the bottom edge. I definitely want to just measure top to top. I know that this is the top over here, and this is the top over here, and I don't want to measure to the bottom to the top up here, even in a 2D view. And then I'll say OK. All right. Now I want to introduce some of the snap and find tools that you see down at the bottom right here. We know to go live is just to see the image that we have right now, and we put our hand in there, we'll actually see it moving. Snap is to grab an image. Find is to actually find some of the tools that you've got set up. So snap and find does both of those, and you can set up to continuously snap and find as well. So let's go back to our GPM, our geometric pattern match, and let's do just a snap and find on that. If we look at the scores down here, it says that it found something in pixel row 291, column 345, and the score is 99. Well, it better be. It's out of 100, and that's great. And the contrast is 99, and the fit error is a small little number. So basically, an angle is 0 because the angle that I taught this GPM is it's only 0 degrees off from it. So it's basically looking back at the master. So that's why it has a score of 99. Then if we come down here to the edge pair tool and do another snap and find, we see that sure enough it found my edges that I trained it to find, and it actually, if I come up to the vision inspection process here and do a snap and find, it'll say evaluation tool not trained. Oh, doggone it, we still have some red down here. But before we can actually do that, we have to give, if I go back to this pixel tool here, do a snap and find, it actually tells me here the length is 285. Well, all this information isn't calibrated right just yet. It's picking out the pixels. It knows exactly how many pixels it is from here to here, but it hasn't converted that to millimeters. Right now, what does it mean that it's 285 pixels. It doesn't really mean anything. First, we have to go back and calibrate it and say how many pixels are there, or how many pixels are there to a millimeter, or vice versa. And to do that, we have to do a calibration, and we look down here and we see that there below our the initial information we set up with exposure is to try and set up the grid spacing, override the focal distance of the lens, and the height of the product from the plane in which it's inspecting, and to actually train this to give it some type of grid snapping. I'm sorry, grid calibration. So what I'm going to do here now is actually replace, put in place where my product is right now, a vision calibration grid that Fanuc produces. Let me do a snap here. And I notice that it's not in place, so I'm going to have to put this in a better position so that we see the 3 large circles and the 2 large circles pretty much in the center. Moving it over a little bit and a little bit in this direction, and it seems like this will be a good place for it to live. I've gone ahead and entered my information here. I'm using a calibration grid that is 15 millimeters on centers from dot to dot. It's 15 millimeters each direction. And then I'm overriding the focal length. And you have the option to do that or not do that. I recommend you do it, and I know that I'm working with a 35 millimeter lens. I've looked at the camera and saw that the focal length is 35 millimeters. Height from plane, I'll leave it 0 for right now, and I'll train this. Say OK. And then yours, because I've already done this once, will be something like this. So you'll just have to make sure you're just capturing no extra artifacts and just surround, try to get a little bit into the white. And surround all the dots. Don't get partial dots. Try and get all the contiguous or full dots that you can by using that window. Once done that, it's going to say the scaling data has been calculated. I click OK. And I see that my scale conversion is 0.15 millimeters per pixel. What that means is that the after it looked at the grid and determined they were 15 millimeters apart, took a snapshot of it, that the distance that each pixel was actually recording when it looked at that was 0.15 millimeters per pixel. Let's try to understand better what that 0.15 millimeters per pixel means. Let's measure from edge to edge of our screen, from the left-hand side to the right-hand side. With mine, I come up with 96.2 millimeters. That's 96.2 millimeters from the left-hand side to the right-hand side. Now let's take a calculator. And let's take that 96.2 millimeters and divide it by our rate of 0.15 millimeters per pixel. And I come up with 640 pixels, which that's what this camera is. The Sony XC56 is a NTSC camera, which is 640 by 480 pixels, 640 across the X direction. So it looks like a pretty good calibration. Let's remove the calibration grid and reset up our T with the background in similar position to where we taught the master originally. Stop live view. And now let's go back and look at, the only thing we have left is the evaluation tool, but I want to check our edge pair to see if it's actually measuring accurately. And you'll see that I've actually set up some values here because I've already trained this. But let me train this again and just show you that I'm going from this edge right here to this edge over here. And if I want to zoom in on that to just make sure I'm getting closer to that edge, I can do that, and it's probably a good idea. It looks good there, and looks good there as well. And remember, I'm not measuring to the bottom edge, I'm measuring to the top edge of the T. I click OK to save that, and now I do a snap and find, and it's measuring, and down here it says it's measuring 43.8 millimeters. If I measure that with my calipers, I see that this actually measures out to be 42.7 millimeters. So now here's something that's not mentioned in your textbook whatsoever, and that's to adjust your calibration. And to do that, I'm going to take those two numbers, that 42.7 and that 43.08, and I'm going to use a calculator. I'm going to divide my 42.7 by 43.08, and I get, it was pretty accurate. It's a 99.11% accurate. But what can we do that to make that actually more accurate? Well, I can look at this 0.150 millimeters per pixel and say, I want to really make that times 0.15 millimeters per pixel. I really want to make that 14.86. So how do I go about doing that? Well, I'll adjust the height from plane, because actually the calibration grid that we used was below where we're actually measuring. And that's what we skipped over earlier. We just left this at 0. And we need to adjust for that now. So this, what we're measuring to right here, is actually closer to the camera than our calibration grid. So let's add the 17 millimeters is the height from the top of the T to the bottom where the calibration grid was. So let's add that 17 millimeters and just hit enter. Don't retrain, because that'll ask for a calibration grid. So I hit enter, and it says the scaling data has been recalculated. Great. Let's click OK. Now let's go back to our edge pair tool, do a snap find, and that did too much correction. Now instead of 43.08, we're measuring 42.06. Remember, we want to get to 42.07. So let's go. That was a full millimeter by putting 17. Let's go back to our calibration grid here, and let's put in say something less than half, even like about 8 millimeters, and hit enter. Click OK. Recalculated the millimeters per pixel to be now 1.149. Let's go back to the edge pair tool and do a snap find. And now we're pretty close. 42.615. That is like 99.99% accurate. I'm going to save this because I like it. So basically what I did there was just find out the difference between, the percentage difference between my actual measurement and what I was getting as a measurement here, divide this into my actual measurement, and come up with a correction factor, and multiply that times this scale conversion, the millimeters per pixel, to make this more or less depending on what our measurement was. And I did that by adjusting my height from plane to correct this scale conversion factor.